about set theory, which is in packet 2 in your Moodle notes. And the set theory starts after the first hour exam review material, so it starts on page 17. And since I got a printer to work, I'll start bringing my printouts of the packets and showing you what they look like. Because these are actually, I'm going over them before class, and I'm going to be talking about them so you can get a preview of what we're going to talk about. Before we go to that, I'm sure that you were thinking about your exam. So let me give you a little bit of information about that. We are not done grading them, but we are working on it. And I have a couple of good things to tell you. You guys did great on proofs. So far, I think the average grade on proofs is like 30 or 31 points out of 32. So excellent job. We are not done grading some of the other problems. So I don't have a good sense of where you guys are, but pretty much problem 1, everything I saw looked good, which was the truth table problem. That's like 3 points. The predicate calculus problem with the truth table, I apologize. The question we asked was a mess. We're being very nice and generous with the points. Okay? It was ridiculous, all those knots, and I apologize. You were probably stressed about that. Don't worry. We are being nice with the grading. Pretty much anything where the stuff you put on the row matches the other stuff you put on the row is going to be marked correctly. If you get your test back and that is not the case, take it to a TA and we will fix it. So it is not our intention to torture you. That accidentally happened. So we apologize for the torture. Thankfully, it's not worth that many points. So it was only worth 10 points total on the exam. So anyway, everything is looking good so far. We believe we will be able to give them back to you on Thursday. But your TAs all have tests too. So they're like, I got to study. And I'm like, no, you have to get the tests back to the students. It's your job. That's why we pay you. And then they go, okay, I'll try. So we'll see. I'll keep beating on them, and we'll get them back to you as soon as we can. So hopefully Thursday, maybe they'll like run in here by the end of class and give them to me, something like that. Okay. Any questions, logistical questions or anything before we get into set theory? Just to let you know, we're going to do a set theory introduction today, and then towards the end of class, I'm going to pass out midterm evaluations. And what those are is the department provides a service of doing midterm evaluations for any professor that asks for it. And they're Scantron sheets, I believe, and you can give me some feedback on how you're doing. So what they will do is they will quickly compile those results anonymously. So I will need a volunteer for the end of class to take these to the main computer science office. And what they'll do is they'll compile them and they'll let me know what your comments are. So please do write anything down that you want to tell me or things you'd like to change for the course or anything. Please be constructive. So if you say something like, this class sucks, I cannot do anything about it. Okay? But if you say something like, oh, I'm so angry because we had to use an overnet. Oh, but it was okay because I got to turn in the paper version. That's fine. Okay? Or something constructive. So if you have feedback that can make the class better, feel free to put it on there. Or you may always also post on Piazza, and I don't know if you know it, but you guys can make polls and things like that. And in fact, we had quite a good discussion on Piazza last year about how to make the class better, which actually happened right after Novanet when people didn't realize that we had limited number of connections and they were mad. And they posted on Piazza, I'm so mad that I have to use this. And I replied, and we talked about ways to improve the class. And I'm happy to do that. So I do like to take feedback and work on it from whatever you tell me. And I've talked to students from the past class, and those who've been doing who did the peer tutoring last fall really enjoyed it, and that was the best thing on my evaluations last year. So I hope that you are taking advantage of the peer tutoring, that other students are making available to you their time and to help you with your homework and their homework. It actually does help. If you're not a peer tutor because you think, oh, I don't want to help other people, you actually learn quite a lot from doing it. One other announcement is that we are getting a space for you guys to do studying together, and it's going to be on the 3rd floor on the opposite side of this building. It should be ready right after fall break. So after that, we'll probably have, all the office hours for the TAs will be there, and there'll be tables for you to work together so you can show up there whenever there's hours. So we'll let you know about that as soon as it's ready. So it's being painted right now. We're going to put the desks and stuff in there. So, we have 250 people in this class and the other class, so we try to provide you with as much service as we can. Okay, set theory. So sets is like nice and easy and relaxing after all the stress of doing the test. So we'll do that. So when we were talking about predicate calculus before, we actually had discussed that we needed to specify, when we were using a quantifier, a universe of discourse. If you remember that funny phrase that I used for who the heck are we talking about. Okay? And when we start to specify a set of things, then we actually quickly need to come up with a notation where we can actually write set notations the same way. And you've probably seen me use set notation before, but I haven't explained it, so that's what we're going to do right now. Okay, so here's what your Packet 2 set theory outline looks like. So it's very bare bones there just for the outline. And then we have some definitions and some practices, some common practices we use. So when we talk about sets, we use capital letters. So when we talked about logic, what size letters did we use? We use lowercase letters for our Boolean variables, right? Except for when your TAs made the test questions, they use capital letters. But most of the time we use little letters, unless we're doing circuits, and then all bets are off. Okay, so but when we're talking about sets, we use capital letters. We use small letters or lowercase letters for elements in a set. So this is a standard set notation. So we have curly braces to let us know what's in the set, and everything that isn't in there is not in the set. There's commas in between elements of the set. And each item in the set is called an element. This member operator means is an element of. And so, for example, if I want to say A is a member of the set A, it's confusing. So we'll say little a is a member of the set big A. That's how we write it. Then we also have a notation for counting how many things are in the set. So, for example, this set A has 3 elements. Now, one thing to note is sometimes when I'm writing a set down, I might accidentally, or maybe on purpose, repeat an item in the set. But when I count the items in the set, I only count each one of them once. So, for example, if I took the list of all of your first names in this class, it is pretty likely that I would have more than one John, and more than one Matt, maybe more than one Sam, depends on the semester, okay? Probably only one Leo. A few of you have unique names, and some of you don't. But if I count all of the different names of students in the class, it would be all the unique ones. So the size of the set of first names would only be the number of different ones that we have. So when we talk about cardinality of a set, we don't count things more than once. And this is a useful concept for computer science because a lot of the things that we talk about with sets are going to relate to databases. So I'm making a very, very large leap of abstraction between sets and databases, but a lot of the things that you will learn if you take a databases course or you do any databases programming are related to sets. And does anybody know why there's a relationship between sets and databases? Okay, first I want to ask you a question. If I give you the set A, does it matter how I write the elements? No, it doesn't matter how I write the elements, A, B, and C. Is that something in common with the database? Yes, because everything in the database is on its own row, and it doesn't matter where I put it, because it's all just in the database, right? I don't have to alphabetize a database, right? You guys know this. Okay, if you don't, now you do, okay? Databases are kept in rows, so if you've never sort of visualized a database, just think of a spreadsheet. Spreadsheets are like super basic databases, okay, where every row is all the information about one person, okay? So order doesn't matter in a set. So it means I can write a list of things. It doesn't matter what order they're in. Every ordering of it is an equivalent representation of the same set. Okay, and that matters too because we're also going to count later when we do counting. We're going to count sets of things, and sets means order does not matter. Okay, so here's our general description of how we write a set, and then we're going to do some examples of some different kinds of sets. So this one is funny. So it's not funny. It looks funny probably to you because you've never seen it before. So this says B is the set containing N so that N is a member of P, and you probably don't know what P is, but it's the positive numbers. So mathematicians have a few sets that they already use letters for, and those letters are P for positive, and you usually, if you're going to handwrite it, you'll put a double bar on the left. We have R for real numbers. We have N for the natural numbers. I always mix up whether natural numbers start at 1 or 0. P definitely doesn't have 0 in it. So whichever one you use, just make sure you're consistent. So this is natural numbers. Z is integers. What's the definition of an integer? It's a whole number. A whole number or? Okay. Okay, so basically they don't have anything after a decimal point. Let's just put it that way. All right. So what about rational numbers? Has anybody ever heard of rational numbers? That's right. Rational numbers can be represented as ratios of integers. So how would we write the set of rational numbers? So I would write it something like P over Q, where P is in Z and Q is in Z. So that is the set of rational numbers. So this is a notation, so I don't have to write down all the stuff in the set. I'm just writing down a definition of what goes in the set. So what's to the left of the vertical bar is sort of like what an element looks like. Well, it's like a variable definition is what it really is. And then the bar just tells me what the definition is, like what kind of thing can go in that definition. So other information you need so you can fill in possible values. Can you actually write all the members of the rational numbers down? Why not? Because there are infinitely many of them. Okay? So the integers, there's an infinite number of them. There's also an infinite number of real numbers, right? Is one of those bigger than the other? Is infinity bigger than infinity? How many people think that one of them is bigger than the other? Okay, how many people think that infinity is infinity and we can't have bigger than at that size? Wow, it's half and half. That's interesting. I'd like you to talk to your neighbor and see if in pairs you guys agree. It looks like you guys with similar opinions are sitting near each other. I don't know if it's like peer pressure or something. I'm just going to raise my hand. Talk to your neighbor, see if you agree. Recording? Okay, so raise your hand if you think that the size of the real numbers is larger than the size of the integers. Okay, hands down. Raise your hand if you think that they are the same size. Okay, so that's less votes than we had before, and the consensus is correct, so the larger majority is correct. the real numbers is larger than the integers. Does anyone know how to prove that? Well, we'll do a back of the napkin proof, and then we'll figure out if we can do a formal proof. Okay, so a first argument is that any pair of integers, there's an infinite number of real numbers in between them. Okay? Any other particular suggestions? Yes. The real numbers contain the integers and then some. That is also correct. Other arguments? Yes.
You list all of the decimals, and you assume you can list them, and then you prove that you can always come up with another one.
That is a great point. So that's actually what I wanted to get to. So what was your name? Nathan. So Nathan suggests, let's assume that we can write down all the real numbers in decimal. Or some other notation. Okay, and then there's a little bit more to that argument. Do you have any other suggestions? Yes. Okay, so we also need to write down the integers. So if they are, the idea is if they are the same size, then I ought to be able to list all the elements of one down the rows of a matrix and all the elements of the other across the columns, and I should have a matrix that will match up all the items in one set to all the items in the other set. Make sense? So I should be able to put integers down the rows and reals across the columns and match them up. If they're similar size, so if two sets are of a similar size, I should be able to do that. Does anybody know what kind of mapping that is called? A one-to-one mapping. So if two sets are the same size, then I ought to be able to construct a one-to-one mapping for the members of the sets, right? So same size, even if it's infinite, implies that we can have something like a one-to-one mapping between the sets. Okay, so there's stuff before these numbers and stuff after it. Okay, so for the reals, let's pick a representation to put, let's just start, like, there's going to be some, and then we're going to list some, right? Let's say 0, 0.001, 0.002, and so on. Okay, whatever representation I put on the columns, there's always a real number in between them, right? I can just take those two numbers, add them together, and divide by 2, and there's a number there. Because reals are what? They're closed under addition and division. Has anybody ever heard that term before, closed under? You've heard it, but you probably don't know what it means, right? So that means if I add or divide reals or multiply them or subtract them, reals are closed under all those, right? But integers are not. Right? So with the reals, no matter where I am, I can add, so no matter what representation I come up with, I can add two adjacent ones together and divide by 2, and there's a number missing in between. That is a proof by contradiction that I can actually do this. Right? No matter what representation I use, any pair of columns of the reals, I can find a column that I didn't write. And that basically relates to all of the arguments you guys made, which is that between any pair, not even just any pair of integers, between any pair of real numbers, there are an infinite number of numbers. Right? So no matter what resolution you get to, there's always a number in between. Because reals are closed under plus, minus, times, and divides. So this is a proof by contradiction I didn't write it all down, and you don't need to because you're not going to write a proof like this. But I wanted to show it to you because this is an important process in computer science of like trying to figure out the size of something by lining it up with something else and then saying, well, if I can make a one-to-one mapping, then these things are the same size. And that's called diagonalization. So what this means is that I didn't fill out this thing. So whatever I said was number 1, I put a 1 there and a 0 everywhere else. And the second one would have a 1 under the second real number. And the third one would have a 1 under the third and a 0 everywhere else. That's why it's called diagonalization, because I'm making a diagonal matrix that makes a one-to-one mapping between the rows and the columns. So let me draw that again to be more clear. So if I want to show two things of the same size, diagonalization, it needs to make an identity matrix that has 1s on the diagonal and 0s elsewhere. And the 1 shows a one-to-one mapping between elements of the sets. So what we said we could do is that we could write the integers down one side. Well, there's dots going off each way, so we can write the reals on the columns no matter what representation we use. So what we were saying is we were actually going to make a one-to-one mapping between these So this is what the whole matrix looks like, which is basically what we call a diagonal matrix, which has only values. So a diagonal matrix is one that only has values on the diagonal. And this is an identity matrix because it only has 1s and 0s. So we have a 1 if those two numbers are related to each other. So that's what we're doing. We're making a one-to-one mapping. So we're listing all the elements of each set, and we're showing which one relates to which. So our proof by contradiction that this mapping cannot be done is no matter what columns I choose, any pair of them, I can prove that I can always find a number in between them, so therefore there is no such mapping. Is there such a mapping between the integers and the rational numbers? So I want you to write down why you think or you don't think there is such mapping between integers and rational numbers.
All rational numbers, and you subtract all integers from those sets, you're going to end up with an empty set and a set that still has numbers in it.
Okay, so the idea is that if I take the set of the integers and subtract the set of the integers, that is going to be the empty set. That's how we write empty set. We also write it like that. But that if we do the rationals, I'm just going to use an R, even though we usually use it for real numbers. I'm not going to put the double bar on it. But R minus Z is what? It's not the empty set, right? Like, for example, all I have to do is say, like, a half is in there, right? Okay. Any other arguments? Yes? So there's an infinite number of ways to represent the integers? Okay. The reason why I'm not happy with that argument is because all the different ways of representing numbers count for only one element in a set. So I'm glad you mentioned that because I want to clarify. No matter how I write an element of the set, it only counts once if it actually has the same base value. So even if I wrote 1 over 1 and 5 over 5 and 7 over 7 and so on, the cardinality of this set is still 1. So all of the different ways of writing 1 still only count as 1 in the set. So that argument doesn't work, but it was a good try. Okay, so you think there's an infinite number of rational numbers in between in between any two integers? We think so. There's definitely more than one, right? Yes. Okay, and did you have a different argument? Okay, so the size of the rational number is about how big do you think it is? Whatever size the integers is, how big is the rational numbers compared to that? Okay, I could represent the rational numbers with a matrix. What would be on the rows and columns of the matrix? All of the integers, right? Because every single rational number can be written as a ratio of two integers. So if I have all the rows are all the integers and all the columns are all of the integers, then every rational number possible should be able to be fit in that matrix. What is the size of that matrix? Infinite times infinite minus duplicates. Very good point. There's not that many duplicates. There are infinitely many of them. So the size of the rational numbers is the size of the integers times the size of the integers minus probably some constant times the size of the integers. Do you care about this? No. Is it on a test? No. Just thought it was entertaining. It's approximately squared the size, right? This is the kind of calculation you want to be able to do as a computer scientist, right? I need to be able to map sets and figure out how big they are. Why do I need to do that? What did you say? So you can allocate resources. What kind of resources? We are computer scientists, so we allocate computer resources, right? Like memory and computation time. Those are our two main resources that we have, and that's what we have to allocate. So what else do we need to do it for? No, I am never asking you whether you have to do something for a test. I'm asking you what the usefulness of something is. If you guys watch any of my recorded lectures on iTunes University, you'll see that there was one guy who sat in the front every single lecture. He'd say, "What is this good for?" And he was like a CEO of his own company. He was taking the computer programming certificate here because he wanted to see what all his employees were doing. And he took my class and he was like, they're not doing this. Whatever it is that they're doing, they're definitely not doing this. So I started working on making sure that I tell you how all this stuff applies. And then he dropped the class, and I did so good after that. It's really no good. But anyway, you also need to test inputs, right? You also need to know how many possible inputs you might have for a program. So, for example, if I'm trying to have someone log in with a username, I need to know how many possible usernames they can have. So why, for example, do we have 8-character logins at NC State? Because a character is 8 bits? No. Because there's way less than 36 to the power of 8 people. And how did you get 36? Letters and numbers put together as all the different choices for each of the positions. It's basically because they needed to allocate all the possible usernames, and they chose a limit that would give them enough variety in usernames, but also enough space for everybody. So there's a trade-off, right? If I only use 2 characters, how many people could I represent? 36 squared, not too many, right? We have a lot more people than that here. So they needed to have enough, and also they need to have something memorizable, right? Like even if they just pick the number of digits we need to represent everybody, who's going to remember a login of 177Z? Nobody. And also you don't want that to be your email address, right? So anyway, you want to think about the size of sets when you write programs. So the set of all the possible inputs you have is something you need to be able to understand and count. And the reason why sets matter is because when I'm thinking about inputs, I'm probably going to get one user is going to log on 17 million times. And so if I look at my list of logins and I want to count like how many different people logged in, I need to think about the size of the set, not the size of the number of logins that I have, right? Right? Because I'm also going to have some people that don't log into anything ever. And they probably don't even come to class, so they don't even get my joke. This wasn't much of a joke. Okay. So anyway, we just need to be able to do this. And also, as a computer scientist, you need to know about diagonalization. So anytime you want to count something, think about lining it up with something you know how to count and seeing if you can make a one-to-one mapping. That is called diagonalization. And the reason why I'm telling you that is because the computer science faculty decided that we should tell you that in discrete math. So now you know. If you're interested in it, there's more in your textbook about diagonalization, and there's some cool resources online too. If you want to know more, post a question on Piazza, and I will post some more, but we're not going to do anything else with it. Okay, so I wanted to show you a few notations that we're mostly not going to use, but you need to know what they are. We're mostly not going to use them because we don't care about real numbers, because there's too many of them for us to do anything with on our computers. Right? Do we represent real numbers on computers? Raise your hand if you think yes. Raise your hand if you think no. Oh, most of you don't vote on this one. That's why you didn't vote, right? Because you didn't know what I meant when I asked the question. So, do we represent real numbers on computers is the question. I did not say all. So do we represent real numbers on computers? Do we accurately represent real numbers on computers? Sometimes. Sometimes we do, because we just decided that there was a whole lot of real numbers, right? Way more than we could ever possibly represent, because even if I have an infinite number of slots to put things in, I can't put all the real numbers in there. Okay? So we can't actually put accurate real numbers on computers, but we represent them with a certain number of bits. That gives us basically a certain number of decimal positions, and that's how much we can represent. Still a heck of a lot, but it's not all of them. Okay, so that's why we don't care about real numbers, because we don't actually do that much with them on computers, and we don't do that much with them in this class, but I want you to know what the notation is. So if you see closed brackets with this notation, this is a set, but it's the set containing all the real numbers between A and B, including A and B, and you might hear something like the word inclusive. Okay? And then this, people don't normally say this out loud, but they might write it. So the set of numbers between A and B, including A, but not including B. And this is the set of all the real numbers between A and B, not including A or B. Right? So you probably know how to draw these in another class. Since we don't care about them, we're not going to draw them. But this one we care about. This is the set with two elements. So curly braces is what turns something into the set. So see, all of these are sets, but this is shorthand notation for a big set. Just tells you what the endpoints are. Okay, so we mentioned the empty set. And we have two notations for it, and they are confusing. And this is what's going to trip you up the most. So I'm going to give you a couple of tools to deal with empty sets. Okay. The empty set is the set that has no elements. There is only one empty set. Because remember that sets, no matter how we write them, they're the same if they have the same elements in them. There's only one that has none. How many elements does that set have? has one element. So when you look at the empty set, don't think 0 or nothing, don't think zilch. Think of it as a container. So set notation is dealing with containers. That's what those curly braces are. They're containers for all the stuff that's inside. If I have a container inside a container, then I have something in the outside container, right? So that's like if I go to the airport and they say, how many bags do you have? Now, how many of you have like cool organizer bags or at least grocery bags that you put your stuff in inside your bags? There's like 4 of you, okay? If you like backpacking, you probably do that at some point. Okay? How many of you have like some kind of toiletry bag in your bag, some other bag inside your bag? Okay? So even if you brought nothing with you, like let's say I'm going to go to Turkey, my husband's from there, we always take a suitcase with us that has nothing in it, except maybe some other suitcases, so we can bring back stuff. Okay? And if I go to the counter and they say, how many bags do you have? I'm not going to say 0. Okay? So if I ask you, what is the size of this set? Please don't say 0. That is the set containing one element, and the element is the empty set. Okay, so the set of all my bags, if I have something in my hand, is not 0. Even if it's empty inside. Okay? So, what you should do is pretend you cannot see inside that bag. Pretend you actually work at the airport and you're not supposed to open it. And you're not part of the TSA. They get to open whatever they want. Okay? So, think of these like suitcases. So if I'm asking you how many things are in here, this empty set, I don't even care what it is. I can write the letter A, and over here write A equals the empty set. Now this is easy to count, right? There's one thing in there. So why am I doing this? You're looking at me like, oh, this is so boring. Okay, because you're going to have problems like this. Okay, how many elements does that set have? I've heard 3 and 2. I haven't heard 5. Okay, 5. 5 is too many by absolutely any measure. Okay, this is what's known as a trick question, and this is pretty much the only kind of trick question I ask in this class, because I want you to know that an empty set is not nothing, okay? But that sets actually only count things once. So these two things are equal, right? So that's 1. This thing is not equal to either one of those because it is a set containing something, and this is a set with nothing, right? Now these two things are equal, but I don't actually care because I only cared about the size of this set. So this, I'm going to treat it like a suitcase. And that's a suitcase, but these two suitcases are the same, so I'm going to cross that one out. Okay? Now inside this suitcase, how many things are there? 1, because they're the same, so I'm going to cross that one out. Okay, now how many does the original set have? 2. This is an empty one, and this is a not empty one. It's Dr. Barnes' husband's bag to go to Turkey. It's a suitcase with another suitcase. And here's our empty suitcase, and here's our suitcase with another empty suitcase inside it. Okay? So count up the suitcases, and you're going to be doing fine. And just make sure that you cross out things that are repeats. Okay, so part of what you need to do is be able to count the size of sets. By the way, sets can contain other sets. It's very annoying, but they can. So I can have a set of sets. So let's write out what is in. Let's say my set is P, and it's going to contain the sets A, B, and C. Okay, so what I'd like you to do is write out what's in P. So I just gave you the definitions of A, B, and C. What are the elements of P? Write it down. And then you can check your answer with mine and your neighbors. So check your answers with your neighbors first, and then we'll check mine. For that, let me just put the answer up. Okay, so P has 3 elements because it has 3 sets that are subsets. So by the way, whenever you see a problem that looks like this and you get asked for cardinality, you can close up your suitcases and count how many suitcases you have. Okay, so we can have sets as members of sets, and we can mix them up. We can have numbers and sets as subsets. Yes? Yes. So 3, 4 is the same as 4, 3. Yeah. I'm sorry. Can you repeat your question?
So like if in the A, B, and C were those two instead,
Mm-hmm.
would you only have 2 elements?
That's a great question. So if A was equal to this and B was equal to this, yeah, it would have fewer elements if A or B or C were equal, but without further information, you would say that the cardinality was 3. So if, for example, A, B, and C were all the same, then the cardinality would be 1. So that is a good question. But I'm not going to ask you any trick questions like that. So I'm only going to give you questions where you can actually count. Unless I accidentally have the TAs make you a question that I didn't check sufficiently. Okay, so we need to have a couple of other definitions done today. So we actually can do something. So if you made a mistake on the last one, which I think most of you didn't, but if you did, you might have thought that we might have been asking about this set. So this is not A and this is not B. We have A, B, and C on our prior slide. So we're going to use these for A, B, and C. So union is when I actually take sets and I put them together to make new ones. So this is a set containing X so that X is in A, or X is in B, or X is in C. And I bet you thought, oh no, I thought I was going to be able to get away from those logic operators. But you can't. Sorry. Okay, so union is equivalent to OR. So I would take 1, 2, 3, 4, 5, 6, and the cardinality of this union is 6 because that's all the unique elements, even though 3 occurred twice. So whenever you are asked a question about size, you want to ask the question, am I counting unique elements or am I counting, how many things? So if you're counting the size of a set, you are counting only unique elements. Yes? That's right. I never count anything twice for sets. Okay, so we also have the idea of an intersection. So an intersection is like an AND. So it is X so that X is in A and X is in B. And that means that the element is in both sets. And looking back at our A and B sets, the intersection was the point 3, right? And so the cardinality of the intersection is 1. Because there's one element that is in both sets. Okay, so we also have a minus. So A minus B, it might be also written like that. So that is all the elements of A that are not in the intersection. So if we put a slash through this member of operator, then that means is not a member of. So that's basically A not B if we use our logic notation. So in our previous example, that would be the set containing 1 and 2. So the results of set operations are new sets. So if I ask you, what is A minus B, you need to put curly braces and then list the elements and put ending curly braces because it is a set. The result is a set, not just a list. Okay, we can also do exclusive OR. So exclusive OR is exactly what you would think it would be. It was X, so the X is in A. And the X is not in B. Or X is not in A and X is in B. Okay, so those are set operators. Now we have a couple of other notations. Well, actually, before we get to that one, let's do the complement of a set. So sets are, lists of things. So when we have a proposition, we just put a bar on top or put a minus sign for the opposite. But since sets are like, not black or white, one or the other, we use a little c to denote the complement. So I'm sure that all of you have seen Venn diagrams before. So a Venn diagram is used to represent a set. So I usually draw a set by drawing a circle. So if I'm going to use a Venn diagram, I draw a circle, and everything inside the circle is stuff that's in A, and everything outside the circle is stuff that is an A complement. Okay, and this square is usually denoted to talk about the universe of discourse, which we have seen before in predicate calculus. It's the universe we are considering. So if A was a set containing numbers, then the universe would be all the numbers I was considering. Let's say it's integers, and say maybe A was just the set 3, 5, and U would be all the integers. So we can draw like this just to show what A and A complement is. So the way I write A complement is the set containing X, so that X is not in A. And it's sort of assumed that X is in the universe of discourse. So it's lovely and wonderful that the universe of discourse looks like a union sign, so put a little foot on your U for universe. Okay, so we have some other Venn diagrams that are easy, and you already kind of know what they look like, hopefully. So if I can draw a set A with a circle and the set B with a circle, if I want to talk about their intersection, I should draw them overlapping. It is possible for the overlap to be empty. So normally when I'm drawing a circle, I'm not thinking about a filled-in circle. I'm thinking about a circle with dots in it. Because when we talk about sets, we normally talk about either finite sets, like with finite number of elements, or countably infinite, which means we can map it to the integers. And so we really think about dots being in here, and if it was empty, I'd have no dots, and if it's not, I'd have some dots. Okay, so this football is A intersect B. Okay, and this peanut shape, this whole peanut shape right here, that is A union B. Now, it's easy to see that if X is a member of A, that is clearly in the union of A and B, right? Especially because of the picture. So that's why we use the pictures, because they help us visualize things that are true about sets. Now, is it possible for something that's an A complement to be an A union B? I'm sorry. So X is an A complement does not imply that X is not in A union B. Okay? So because it could be here, right? That point right there is an example of something in A complement that is in A union B. Because stuff can come from B that actually doesn't overlap with that, yes. Thank you. And like I said before, we have not escaped from our logic, so we actually have De Morgan's with sets. So if we take the complement of something, let's say we have A union B. If we take the complement of that, well, if we drew our picture of A and B and the universe, then the complement's out here, right? This is B complement, that's A complement. This is A union B complement. Can I figure out what A union B complement is from these? From A complement and B complement? You don't think we can figure it out? Yes, what is it? That's right, it's the intersection. So if I thought of these like slides and I slid them over each other, then the stuff that was in both of them is outside of the union, right? So the stuff here and the stuff here, if they're in both of these, then that means they're not in the middle there. So that's equal to A complement intersect B complement. Lovely, looks exactly like De Morgan's because it is De Morgan's with a new set of symbols, right? Remember, union is like or. And intersection is like and, because they actually are ors and ands that are inside set notations. And so the knots work the same way. So De Morgan's actually works the same way. So the complement of a union is an intersection of the complements. And it works the same way for intersection too. So the complement of the intersection is a union. Oh, there's one other rule that we need to do, and it comes straight from logic also. Union and intersection are associative and commutative, so A union B is equal to B union A. This is specifically because order doesn't matter. So it doesn't matter what order or how many times I've repeated something. So it doesn't matter what order we do, and it's also associative, so A union B union C, it doesn't matter where you put the parentheses. So if we're going to do three things, three operators, as long as they're the same, we can move around the parentheses wherever we want. A union A is equal to A. A intersect A is equal to A. Easy stuff. A union the empty set is what? It's just A, because union, by definition, says all the elements that are either in A or in the second set, but the second set doesn't have any elements. So all the elements had to come from A. What is A union A complement? It's the universe of discourse. And what is A intersect with the universe? A. Good. So this stuff is basically as straightforward as it looks. If you take the complement of the complement, you get the setback, so double negation works. Okay, we can define sets that come up with empty sets, but looks like it's time to give out the midterm evaluations. So we'll stop here. And we'll see you next time. So can I get a volunteer to...